Next, we want to look at coordinates and bases, and this will be why everything is pretty much Rn. Let's consider a vector space that is not Rn, but we're going to make it look like Rn. So P2 is the set of all polynomials of degree 2 or less. The standard basis for P2 is 1, t, and t squared. Every polynomial, so it's a basis, that means it has to be a linearly independent spanning set. So every polynomial of degree 2 or less is a unique linear combination of these three polynomials. In this case, we're looking at the polynomials as vectors. We're thinking of polynomials as vectors. So for example, so every polynomial of degree 2 or less is a unique linear combination of these three polynomials. So for example, if I write just some polynomial, p of t is 3 minus 2t. I can write that this is a unique linear combination of these three vectors, 1t and t squared. If I take 3 times this first one, minus 2 times the second one, plus 0 times t squared. So I can say it's 3 times 1 minus 2 times t plus 0 times t squared. And that's the only way to write it as a linear combination of these three polynomials. So what this means is we can write the coordinates of P relative to this standard basis. Oh, I need to name the basis. A lot of times for bases, we use script capital letters. So fancy B is the name of this set. Notice that fancy B is only these three vectors. I'm not saying that P2 is equal to 1t and t squared. P2 is all the polynomials. Standard basis for P2 is these three vectors. A lot of times when we're trying to abbreviate, we don't want to type so much or write so much. And not wanting to write so much translates to not wanting to type so much, even though we're just typing instead of writing. And so you just be like, oh, P2 is this. And I'll be like, oh, nah, P2 is way more than just those three vectors. But if you tell me this is the standard basis for P2, yeah, that's only three vectors. So the coordinates of P of t relative to the basis script B, fancy B. Oops. We put brackets around the polynomial and we put a subscript with the name of the basis. The brackets around the polynomial kind of says, we're going to make a vector out of this. And then the subscript B is saying, this is the basis we're going to use. And it says we need 3 times the first vector, minus 2 times the second vector, and 0 times the third vector. So that would be the coordinates of P relative to basis B. Notice that this makes P of t, a polynomial, look like a vector in R3. So now polynomial P in P2 looks like a vector in R3. So, like we saw on the Canvas page for vector spaces, what do we need to know about vector spaces? We want to describe the vector space with a basis. We want to come up with some kind of basis to describe the vector space. Then we want to take anything in that space and write it as that unique linear combination of the vectors in the basis. Then we'll have coordinates that look like Rn. And so that's why everything is pretty much Rn, because we want to establish a basis so that we can establish coordinates. Now, we notice that the dimension of P2 is 3, because there are 3 vectors in a basis. Notice that I didn't say there are 3 vectors in the basis. I said 3 vectors in a basis. There's more than one basis for any given vector space. Let's look at an example. Any vector space, some of you are going to start being picky at me too. Any non-zero vector space will have lots of bases. So for example, the standard basis for R2 is 1, 0, 0, 1. R2 is 2-dimensional. I need 2 linearly independent vectors from R2, and that will be a basis for R2. Any 2 linearly independent vectors in R2 will form a basis for R2. Any pair of linearly independent vectors in R2 can be a basis for R2. We just use 1, 0, 0, 1 because that's the easiest one. That makes the easiest graph paper. So let's take a look at, what did I use for inverse of a matrix 1? So let's make an alternate basis. Let's suppose I had 3, -2, and -7 and 5. Oops. Making a set of vectors, not a matrix. 15 minus 14, that's going to be 1, so that'll work. That's easiest. This set of vectors is also a basis for R2. Everything in R2 can be written as a unique linear combination of these 2 vectors, 3, -2, -7, 5. So for example, let me grab one completely at random. Oh, actually I do. So for example, the standard coordinates of this vector could be, say, 1, -1. Well, let's find the coordinates of P relative to the basis B. That is, write 1, -1 as a linear combination of 3, -2 and -7, 5. So I want to write x1. I need to turn the page. Uh-oh. There we go. So I need to solve the equation x1 times 3, -2 plus x2 times -7, 5 equals 1, -1. That is, we're going to find the reduced echelon form of an augmented matrix. So while I'm punching this into my calculating machine, think about how I knew that I was going to have pivots in the first row, first column, and the second row, second column. So I'm going to have pivots. I knew I was not going to have a pivot in the rightmost column of this augmented matrix. So 3. Yep, I knew that that was going to happen because the columns of that matrix, 3, -2, -7, 5, which I haven't named yet, but we could call A. The columns of that matrix will be linearly independent because there's only 2 columns and one is not a multiple of the other. So 3, -7, 1, -2, 5, -1. So the reduced row echelon form has a -2, -1. So what that means is if I take -2 times 3, 2, minus 1 times -7, 5, I should come up with 1, -1. We can check that that's going to be the case. I'm doing this because I want to reinforce the ideas that go all the way back to the beginning of this class. So I got -6 plus 7 is going to be 1, and 4 minus 5 is going to be -1. That's just showing that this checks out, that 1, -1 is -2 times the first vector plus, minus 1 times the second vector. What we would say, so P was the vector 1, -1. The basis B for R2, the alternate basis that we were using is 3, -2, -7, 5. And so the coordinates of P relative to this basis are -2, -1. We could think about this alternate basis as just some kind of weirdo graph paper. So this is going to be strange graph paper, but okay. I can make these lines on a graph and still cover all of R2. So normally, I do this every year, and it's always a bad idea. So normally I have x1, x2. So x1 is going to be the axis for 1, 0, and x2 is the axis for 0, 1. And that's the grid that we want to make. But now I'm going to make some weirdo graph paper where one of my vectors is 3, negative 2. So I'm going to go out 3 and negative 2. And so my first axis is going to go in this direction. And every 3, negative 2 is going to be one of these 3, negative 2s. So put this one back here. So in normal coordinates, we call this 3, negative 2. But in B coordinates, we just call that the first vector. That would take the place of 1, 0. Then I have this vector negative 7, 5. So negative 7, 5. Oops. It's not going to be, I'm going to try, I should try to at least get them kind of in the same place. So this is 3, 6, so 7, and then this is 2, 4, and then so 5. Do I regret this choice of vectors? Yes. Am I going to press forward anyway? Yes. Like I said, every time I do this, it ends up being a bad idea. But what we're doing is now making graph paper, and these are our two axes. This is our alternate axis for x1. So this would be our first coordinate. Let's call it b1. And this is our axis, and that's the positive direction. And here's the positive direction for our axis b2. Now this is really weird graph paper.
I have a question.
Yes.
If we consider the ax equals b, so the p it's gonna be the x vector, and the b it's gonna be the matrix A, and the p sub b it's gonna be the b vector.
Yes, if we take these two vectors, 3, negative 2, and negative 7, 5, and put those into a matrix A, that's a great question. Here is the vector equation. What is the matrix equation going to look like? So if we make A the matrix 3, negative 2, negative 7, 5, just the columns of A are the vectors in the basis B. Notice that the x1 and x2 are being multiplied by A. So I'm taking A, negative 7, 5, multiplying that by x1 and x2, and that should come out to be 1, negative 1. So if I take the matrix A and multiply by the coordinates of P relative to B, that will come up with the vector P. So yes, that's exactly what it would look like in a matrix equation. Take a matrix, the matrix A made up of the basis vectors, multiply by the coordinates, and then you'll come up with the standard coordinates. The columns of A are standard coordinates of the B basis vectors. If I multiply the columns of A where that are the standard coordinates of the vectors in the basis B. Notice that that pops out the standard coordinates.
So in other words, can we say that the P sub B, it's gonna be a vector, and that makes the matrix A the augmented matrix?
No, A is not an augmented matrix because we're multiplying A times the coordinate vector of B. So the augmented matrix for this equation, augmented matrix goes with an equation. The augmented matrix for this equation is just A, and then we put P over here. The reduced echelon form of the augmented matrix will give us the identity here because A is a basis. And then on this side will be the coordinates of P relative to B. All right, let's pause the video here and then come back with some more examples.